Welcome to Linear Algebra, section 1.7, Linear Independence. So before we talked about linear combination, I hope you guys remember what a linear combination is. Now we are going to talk about linear independence of vectors. A set of vectors v1, v2 up to v sub k in the space Rn is said to be linearly independent if the vector equation, this vector equation, c1 v1 plus c2 v2 plus so on plus ck vk is equal to the zero vector has only the trivial solution. What will be the trivial solution? That all these coefficients or the unknowns c1 c2 up to ck, they are zero. Each one of them is a zero. If there are also non-trivial solutions, then the set of vectors from v1 to vk is said to be linearly dependent. So when will the matrix columns will be linearly independent? The columns of a matrix A are linearly independent if and only if the equation Ax is equal to 0 has only the trivial solution. So remember, this equation is the same thing as the equation, vector equation up there. This is this matrix equation. Now note something here. A set of one vector, say v, is linearly independent if and only if the vector v is not the zero vector. So you can have any vector in one single vector, let's say in R2, you can have 2, 3. This is linearly independent. A set of two vectors, say v1, v2, is linearly dependent. So they are linearly dependent if and only if one vector is a scalar multiple of the other vector. The set is linearly independent if and only if none is a scalar multiple of the other. So this one shouldn't be there. So if none is a scalar multiple of the other. And number 3 is a set S is equal to v1, v2 up to vk is linearly dependent if and only if one vector in the set can be written as a linear combination of the other vectors. So if we have one only, even if we have single one vector which can be written as a linear combination of the other vectors in the set, then that set is linearly dependent. Number 4, if a set contains more vectors than there are entries in each vector, then the set is linearly dependent. So if there are more vectors than entries in each vector, the set will be linearly dependent. If a set S is equal to v1, v2 up to vk contains the zero vector, then the set is linearly dependent. So either it contains a zero vector, or if it has a, so these are the three things that you need to remember about linearly independent or linearly dependent vectors. That if there is a zero vector in the set, then that set is linearly dependent. If there is a vector which can be written as a linear combination of other vectors in the set, that set is linearly dependent. And the third thing, that if there are more vectors than the entries in one single vector, then the set is dependent. So here is an example. Say it's determined by inspection if the given set is linearly dependent. So the first example A, 1, 2, 3, 4, there are 4 vectors, entry in each, 3 entries in each. So this is dependent, linearly, this is linearly dependent. Second one, here we have three vectors, three entries, but we have the zero vector. So zero vector in there, so linearly dependent. Okay. Now this one, we have two vectors, but there are four entries. Now we have no condition in, you guys saw here, we have no condition which talks about what if the number of vectors is less than the entries. We don't know about that. Okay, so we cannot say that that will be linearly independent or linearly dependent. But when we look at these two, at the, you know, one when you look at it once, you may not be realize it, but if you notice, if I call it u and I call this v, then if you multiply u by 3 halves, negative 3 halves, you will get v. So we can say that v is a scalar multiple of u, so linearly dependent. You can check that. Okay, next example, determine whether the given vectors are linearly independent. Now you should be able to see that we cannot do it by inspection because none of those conditions are satisfied. So we have to do our work. So what are we supposed to do? We want to find C1, C2, C3 such that C1A1 plus C2A2 plus up to C3A3 is equal to 0. Then we have to solve this vector equation. With this vector equation means C1 times the first vector plus C2 times the second vector plus C3 times the third vector equal to the 0 vector. But solving this is the same as doing the row operations on the augmented matrix, which I have on the left. But instead of doing the operations, we notice here that the coefficient matrix is the lower is a lower triangular matrix. Why lower triangular? Because the non-zero the zero entries are above the triangle, the main diagonal. So if I think of this as the diagonal, the zero entries are above the diagonal. So we can do the back substitution. So if we read each equation, the first equation gives us negative 3c, 3 is equal to 0. Because remember, this is C1, this is C2 column, and this is the column for C3. We have negative 3C1 equal to 0, which I have here. Then the second row gives me 5C2 plus 4C3 equal to 0. And the third row gives me 3C1 minus 8C2 plus C3 equal to 0. And you solve and you will see that you get C1 is equal to 0, C2 is equal to 0, and C3 is equal to 0. That is the only solution, which is the trivial solution, so linearly independent. The set is linearly independent. Okay. Now this is something which has been postponed by me for not for any specific reason. But these are algebraic properties of vectors, you can say, or of Rn. So what is in Rn? Vectors of this type. Okay. Or you can say Rn consists of points or tuples and tuples. Okay. So now we have these algebraic properties, and I will show you how to some of these, how to prove them. So you should be able to do the proofs, because this similar things will come up later in coming chapters. So if you understand how to do the proofs here, then it will be easier for you to do the proofs. And you will notice we will have some things other than Rn type thing, but these properties will be very, very similar. So the first property is what we call the commutative property. By the way, here is for all u, v, w and all scalars c and d. So u, v, w are where they are coming from Rn, and c and d are scalars, means they are real numbers. So u plus v is equal to v plus u. This is called the commutative property. If you recall that we can switch, whether we add u into v or we add v into u. This is not, this may not be true with everything, but with real numbers we know it is true. So I have shown the proof down here. So u is equal to u1, u2, un. First, I think let's go over these properties, then we will come to the proofs. So number 2 is that u plus v, first you add the u and v vector plus w, then you add the w vector. Would give you the same answer if you had done v plus w first and then added u into it. So this is called the associative property. Third is u plus z is the zero vector is equal to zero vector plus u, and this is equal to actually the u vector. Gives you back the u vector. So 0 is a number or is a value or is a quantity which added into the any vector will give you back the vector, and it doesn't matter in which order we add it. This is called the additive property of identity. So the zero vector is the identity vector here. This is identity. Additive identity, we say it. Additive identity vector. Fourth property, u plus negative of u or minus u is equal to the negative u vector plus u, and it gives you the identity vector or the zero vector. So this is called the additive inverse property. So the negative u is called the inverse vector of the u vector, additive inverse. So negative u is the additive inverse of u. What will be the additive inverse of v? Negative v. Additive inverse of a vector a will be the vector negative a, and so on. 5. C times u plus v is equal to cu plus cv or cv plus cu, and this is called the distributive property. In the same way, number 6 is c plus d times u equal to cu plus du. This is also distributive property. Then number 7 is c times du is equal to cd times u, and it's equal to, actually sometimes it's a cd u. And then number 8 is 1 into u. 1 is again a scalar, into u will be just u. It's common. So now what I have done, I have shown you the proofs of property 1, 3 and 5, and I might ask you to do some on your own. So how do we prove it? Well, first let's say u1, u2 up to u and v are two vectors that we are going to use here. So let u is equal to u1, u2 up to un, v is equal to v1, v2 up to vn. Then the first property says u plus v is equal to v plus u. So how can we prove it? Well, we will use the commutative property of numbers, basically. So we start with one side. You can start with any side, this one or that one. Usually we call it the left hand side. and this will be the right hand side. So I start with the left hand side, which is u plus v. Using the definition of vectors, I say this will be the vector u1, u2 up to un plus the vector v1, v2 up to vn. But we know by addition of vectors that we can write this sum as u1 v1, u1 plus v1, u2 plus v2 up to un plus vn. But now because u1, u2 up to un and v1, v2 up to vn are real numbers and real numbers commute, so we are commuting them. We can write them as v1 plus u1, v2 plus u2, up so on, vn plus un. But what is this? This is just v plus n. So we can write it as the v1, v2 up to vn plus u1, u2 up to un. But what is this? This is v and then u, v plus u. So hence we have proved the property. So number 3 is saying u plus 0 is equal to 0 plus u and is equal to u. So we start with the left hand side. We get u plus 0 will be the u vector, u1, u2. What is the 0 vector here? The vector which has n number of rows and one column. So 0, 0, 0 up to last one is 0. Every entry is 0. So when, by addition of vector, it means u1 plus 0, u2 plus 0 up to so on, un plus 0. And then we end up getting all of these give us back u1, u2 and un, which is the u vector. Now we do it the other from the other side, right hand side. So u plus 0 plus u, following the same technique, we end up getting u. So we are getting both. Left hand side gives us u, right hand side gives us u. It means left hand side and right hand side are the same, which means u plus 0 is equal to 0 vector plus u vector is equal to u vector. Hence proved. Fifth property here was c times u plus v is equal to cv plus cu, or cu plus cv. So here I have this property written and I start with the left hand side, c times u plus v. What does that mean? First we add the vectors. So here is the addition, added vectors and multiplied by c. What does that mean? By scalar multiplication, this constant gets multiplied with each entry of the vector. So here I put it with each entry, and then using the distributive law of numbers, of real numbers. So here we have used distributive law of real numbers. But now I can rewrite this as vectors cu1, cu2, c up to cun plus cv1, cv2 up to cvn. But then I can pull out the c from this vector and I can write it like here, c times the vector u1, u2 up to un. And similarly, same thing I can do with the hairs, pull out the c, write the vector left over. And but what is this? This gives us, this is the u vector, this is the v vector. So we end up getting cu plus cv, which is what we wanted to show, which is the right hand side. So hence proved. So this is how you prove these properties of the vectors. Okay, the next section 1.8 talks about the linear transformations.